Okay, I think it's time to start. So we have two talks this afternoon, and the first talk is given by Philippe Ruelle from Université Catholique de Louvain, and he will talk about a case study on the tangent method applied to two periodic Aztec diamonds. You can start.
Okay. So let me first thank all the organizers for setting up the workshop and for the invitation. I think that we all have the same feeling here. Being in Florence is a real pleasure. So yeah, the talk will be concerned with, it no longer works. Yeah. So the talk will be all concerned with Arctic phenomena in general, and in particular special phase separation phenomenon. So by which a certain random model can have qualitatively different behaviors in different regions of the domain. So in many cases, we have examples where frozen regions are next to temperate regions, which are entropic and which contain randomness. And this phenomenon is accompanied by the emergence of limit shapes, which is somehow the fact that the interfaces between the different regions become deterministic curves in the scaling limit. So I think that historically the first example of this was found in the domino tiling of standard Aztec diamonds, not the two periodic ones. But since then, there have been many instances of such phenomena. So hexagons, 6 vertex, alternating sign matrices, 2 periodic Aztec diamonds, which I will discuss today, young tableaus and so on, 20 vertex models that Philippe has discussed 2 days ago, sorry. So clearly, a number of those topics have been discussed quite a few times in the previous weeks and earlier this week. There'll be some overlap, but I think not too much. And in any case, the talk will be very elementary and mostly visual. So Philippe has talked earlier this week about the tangent method, and of course I will come back to it. But we'll present it in a different way and show a different way to have it working. So let's start with the beginning. So that's an Aztec diamond. That's the typical shape with these corners around the 4 boundaries. And we say that the Aztec diamond has order n if there are n corners on each boundary. So the basic question is to ask ourselves, what are the possible tilings of this domain by dominoes? So that's the first question, and we will equip the set of dominoes tilings later on with a probability measure. But for the moment, we just look at the problem of tiling this domain by dominoes. And here are 2 examples, possible tilings for diamond, Aztec diamond of order 6. So the left one is the wholly horizontal one. It's one of the simplest, and on the right one is a more involved tiling. In this case, there are about a bit more than 2 million possible tilings of this domain, and in general, the number is well known. It's this for order n. It is this power of 2. An interesting property is that the set of tilings on the set of tilings, there's an operation which is the flip, which consists in flipping 2 parallel dominoes from horizontal to vertical or vice versa. And this flip is actually transitive on the whole set of tilings, so that any tiling can be obtained from any other by a sequence of flips. And that's a useful property, actually. It's also useful to color the tilings because it shows somehow more structure. So for a given tiling, we first put dots in the domain in this way, these dots will eventually be the vertices of the dual graph of the domino of the Aztec diamond. Then we remove half of the dots, and then we by doing this we see that every domino contains exactly one dot, and this dot can be either on the left or on the right part of a horizontal domino, or on the bottom part or the top part, and that yields 4 varieties of dominoes, and we color them according to where the dot is. So green for this kind, green, red, blue, and yellow. And so we end up with the pictures that probably many of you have seen before, these 4-color tilings. So we'll be interested in the typical behavior of the tilings for large size. And the first observation is that the typical behavior will depend on the probability measure that we set on the set of tilings. On the left figure is simply a uniform measure, which means that we pick one at random, and all tilings have the same weight. And the case I will be interested in this talk is the superiority case, which I will define a bit later. And you see a substantial difference. That's for n equal to 200, and for higher order, the characteristic gets sharper. So we clearly see that in both cases, they are frozen regions somehow, yeah, which are the corners, and on the corners, you find only one variety of dominoes. That's true for both measures. What we can see also is that the central regions somehow contain randomness, and in particular, in addition, they are non-homogeneous. In particular, if you go close to the red corner, you see that the density of blue dominoes is higher, and it's the same feature for the other corners. So the central region is not homogeneous. And what we can also see is that when n gets larger and larger, the interface between the frozen region and the central region gets sharper and sharper. And on the left, for instance, when the order gets to infinity, this interface converges to a circle, which is the result of the famous Arctic circle theorem. It's a bit different on the right because you also see somehow a curve emerging, but a new feature in this case is that you also guess a central region which is different. So you seem to have 3 different regions: frozen corners, some type of entropic region here, and in the central one, another type of behavior. And our objective here is to compute the Arctic curve in this 2-periodic case, and we'll be primarily interested in the interface between the frozen regions, the 4 corners, and the first entropic region here. Actually, we'll get the second Arctic curve for free, but that's not part of the game somehow. So these curves are well known. That's I think that to the best of my knowledge, Philippe was the first with Rodrigo Soto Carrido to compute these curves by techniques which will be actually very close to the ones I will present. And these have been re-obtained later by other people. I'll say a word about that later. So there'll be nothing new in this talk, except that the way we'll get the Arctic curve. Okay, so question is how do you actually compute the Arctic curves? So one of first perhaps naive ideas is to pick a relevant observable that might act as an order parameter and compute the probability. So for instance, in the Aztec diamond, you pick the probability to have somewhere a green domino, and you quickly see that the probability will saturate to 1 in this region, to 0 in these 3 corners, and to some numbers between 0 and 1 in the central region. So if you can compute that, then you will automatically determine the Arctic curve. because you'll see a jump in the behavior of this probability. But somehow that's the hard way. It's the hard way, it's more difficult, technically more difficult, but it also yields more information. A somewhat softer way to compute the Arctic curve is the proposal made by Filippo and Andrea in 2016, which is since called the tangent method. So in a few words, it is based on the formulation, so a description of the tilings in terms of non-intersecting lattice path. And that's in many cases that is available. It's a heuristic approach, but which has been successfully checked in many cases. This approach is much easier than the hard way, which was the first point. But the drawback somehow is that it relies on a certain number of assumptions, which are not always under control. So it requires the description in terms of non-intersecting lattice paths. So let me comment a bit about this and what we can do for the case of Aztec diamonds. So of course, the description in terms of lattice path will depend on the model we consider. There are usually several descriptions in terms of path, and that really helps because one description will usually yield a portion of the Arctic curve, and the other portions will be got by using the other available descriptions. And essentially, the paths are non-intersecting, random directed walks made of a set of elementary steps with starting and ending points which are fixed, namely which are independent of the configuration you look at. And for Aztec diamonds, the description is well known. It is recalled here. So for the 4 varieties of domino, you draw on the blue ones a diagonal step upwards. On the yellow ones, you draw a diagonal downwards step, a level step on the red ones, and no step at all on the green ones. And you end up with this kind of description. And that's, of course, holds for any measure that you could equip the set of tilings. That's only a description of the tilings in terms of path. So for the tiling of an order n Aztec diamond, you get a set of n paths which are non-intersecting, always starting on the left boundary at this point and ending at the right boundary at those points. Those are completely fixed. Right. So in the case of Aztec diamonds, we have a bijection between the set of n upples of non-intersecting path. And the paths are made of 3 kinds of steps, which are here: diagonal upwards, diagonal downwards, and level, starting and ending at fixed positions. Okay, that's what we have to remember for what follows. Yeah. Yeah, that's right. Yeah. Okay. Yeah, that's a good point. For simplicity, I just skipped that. No, because I think his remark is that if you use these 2 steps, you could go from here to here and then exiting the domain, but that is not allowed. So the additional thing that I forgot to say is that this path must be only contained in the domain. So that's that was the content of Philippe's remark, I think. So if you look at the Arctic phenomenon in terms of curves, then what you see is this. So the corners here are maximally packed regions of path. So blue is wholly diagonal upwards, yellow is wholly diagonal downwards, parallel horizontal path here. And in the green region, there's nothing because the green dominoes carry no step at all. And what you see is that the Arctic curve will in fact correspond in the scaling limit to a fraction of the uppermost path will accumulate and condensate on a single line, which will become deterministic and form the Arctic curve. So the Arctic curve will really come from the condensation of all these upper paths onto a single line, making a sort of impenetrable barrier. Okay. So that's it. Yeah, I just want to stress that in this particular case, you see that the uppermost path, so the upper with probability 1 will exit the left boundary at the midpoint and make another contact with the other boundary facing it at the midpoint as well. So the tangent method, in a few words, the main idea would be this. So the most upper path I just said would will quit this left boundary at the midpoint, but the question is, what if you force it to leave from another point? So from P, for instance. And this is a simulation of such a situation, and you will see in terms of path that something interesting is happening. So this path, which is forced to leave from P, enters the domain along what appears to be roughly a straight line, and then hit this bulk of path, which is soon be the Arctic curve in a sort of tangential way. It's not very clear on the picture here, but that's the observation that Filippo and Andrea made. And two essential observations about this are here. So first of all, the fact that you force this path to leave from an unnatural point does not affect the shape of what has become the Arctic curve. So the shape of the Arctic curve is actually preserved by this. And then I said it already. This path will travel in this empty region along a straight line, and then will hit the Arctic curve at a point tangentially. And so that's the basic two observation to formulate a little bit more precisely the tangent method, which is essentially based on these two hypotheses. So first of all, if you perturb the upper path or a finite number of upper paths, it actually has no influence of what the other paths do. And in particular, the shape of the Arctic curve is maintained, is preserved. So that's the first hypothesis. The second one is concerns the shape of this perturbed upper path, which is first of all on a straight line and then touches the Arctic curve tangentially. And then from there on, if you imagine that it touched the Arctic curve here, it will follow the Arctic curve and then go straight to its endpoint, which is here. All right. So H1 is the tricky hypothesis somehow, because it's strong and at the same time it's reasonable, but it's barely controllable somehow. You would certainly believe in it if the interactions between the paths were not too strong, but if you have a case where the interactions between the paths are stronger, then this could fail. And the H2 is not as strong, and perhaps it might look surprising, but in a sense it is expected. Both the linear path is expected because that's the region where the path travels an empty region, and the most likely trajectory will be a straight line. And then it will try, for the same reason, it will try to reach its endpoint in the quickest way, and therefore will stay as close as possible to the Arctic curve. And in the scaling limit, it will actually follow it. Okay, so and we have somehow made general arguments as to why the H2 should be all right. Now, if you take these two hypotheses together, then you actually found an efficient way to compute the Arctic curves. And here is how. So you fix a point P where the upper path will exit this boundary. Then what you have to, well, you have got to compute something on the lattice. And what you have got to compute is what is called the refined partition function, which is namely all the configurations or all the tilings of the domain such that the upper path leaves the boundary at P. That's what we call the refined partition function. And then try to extract from this information the slope of this straight path, this straight path. And then if you can achieve that, and it's at this stage, it's not completely clear that you can do it from this information alone. But if you can do that, then the trick is to vary the point P so that you get a family of tangent lines, of tangent straight lines to the Arctic curve that you can retrieve as the envelope of this family. And so here, the program seems to be clear, but we are facing two obvious problems. First of all, how do you compute the refined partition function? So you fix the exit point of the upper path, and then from that information, how do you extract the slope? So the refined partition function. So you want the upper path to exit the boundary at some prescribed point. Now, in terms of the isomorphism between the path and the dominoes, it's clear that the exit point will be the point where on the western north boundary, the domino change from being vertical to being horizontal, and that's exactly the point where the path will exit. So reformulating the problem in terms of domino, we've got to compute the number of configurations such that along the west-north boundary, you have got k vertical dominoes and the rest being horizontal automatically. And so that's the quantity we want to look at, we want to find. Okay, so k is the number of horizontal domino starting from the left side. Well, that's just an aside remark. We need k to be bigger than the midpoint, because if you force the point to exit the boundary before the midpoint, all the other bulk path will push it and will push it to the boundary. So in the scaling limit, that amounts to nothing. It will still follow the left boundary. So this quantity Znk is the basic quantity we want to compute from the lattice. And for standard Aztec diamond, it's not so difficult. You get exactly this expression. And the problem, what for the two periodic Aztec diamond? So I think the time is for defining what we mean by two periodic measure. So it's a non-uniform probability measure on the set of tilings. And it's better described in terms of the dual graph of the Aztec diamond. So here is the Aztec region, and in red, you see the vertices and the edges of the dual graph. And so each time you have a domino somewhere, let's say on the top, like here, it will cover exactly two vertices of the dual graph, which you mark as a blue bar, and which you call a dimer. And in this way, a domino tiling is in one-to-one correspondence with a dimer configuration on the dual graph, or what is called is a perfect matching. Now, the two periodic Aztec, the two periodic measure will be defined in this way. You mark the faces by A and B so that each dimer will touch exactly one of those faces. And the dimer will get the weight of the face it is adjacent to. Okay. And so that's what is written here. And of course, the total weight of a perfect matching is the product of the matching of all dimers. Good. So now, how to compute the partition function? First, for the standard Aztec diamond. And here there's a nice idea from Kuo in 2004, which proves that the standard partition function, so plainly the number of Aztec of tiling of the Aztec diamond of order n, satisfy this quadratic recurrence. And it actually follows these two terms, of course, are equal, but they have slightly different origin as being the consequence of this graphical equation somehow, by which you think that you superpose an n-2 and an order n-2 and an order n, so the tilings of an order n and of an order n-2 configuration, and you decompose the result into either the superposition of two order n-1 Aztec diamonds in this way, so slightly horizontally shifted or slightly vertically shifted. So I can give a sketch of the proof here. It's really a beautiful argument, and which will be soon generalized to a more general case. So here is an order n perfect matching, an order n-2, and you superpose the two, and you see that what you get are the double edges when two edges are on the same, or two dimers are at the same place, or else you get loops because these two will form a loop with those two, open path, and then single dimers. And that's already what that's always what you get. And now you forget about the colors. You get this, and you soon realize that if you forget about the colors, you don't really you don't really know, in particular for the loops, which tiling or which perfect matching gave which edges, because these two could have been turned around, these two could have been turned around, and you would get the same uncolored loop, which means that for every loop you get a factor 2, and in this case you have a 2-to-1 correspondence. Now you try to redistribute all the dimers here into two order n-1 perfect matchings in this way. In this way, either shifted horizontally or shifted vertically. So if you try to do this, you first try the slightly vertical shift, which means that there should be an Aztec diamond located in this way. Now, what will decide whether the shift is vertical or horizontal is actually the way the open path connect opposite boundaries. And you can see that in this case, this is not possible. And the reason is that it's very simple. You count the length of this open path, and it's a knot number, and these two as well. It's a knot number, and it's always the case. The open path always have a knot number of steps. Now, if you want to distribute the dimers into two different perfect matchings, you'd better not keep two adjacent steps in the same perfect matching, because otherwise the middle point would be covered twice. Which means that since the length is odd, the first and the last edges must belong to the same perfect matching of order n-1. So this is not possible. The right choice is this one. And then you start collecting the various edges in the purple domain here to get that. So the double edges you equally distribute among the two perfect matchings. For the open path, you do as I said, you take one. You take every second one starting from one extremal. And for the loop, again, you equally distribute among the two. Now you do that for the other as well, and you get that. And if you superpose the two, you get this, which is exactly which is a color version of what of the uncolored configuration we had there. And again, there's a 2-to-1 correspondence because when you distribute the dimers of a loop into the two subgraphs, you have two choices. Again, you take for one perfect matching, you take every second dimer, but you don't know where to start. So there are two possibilities for each loop. And so you get in this way a bijection between the pairs of perfect matchings of order n and n-1, and pairs of perfect matchings of order n-1 in possibly two positions. All right. Now, the other beautiful observation made by Spire in 2007 is that this recurrence, this quadratic recurrence, is actually valid in a much more general situation, namely for much more general phase weightings. And that's what he called the octahedron recurrence. And we heard about it this morning since Rinat, the octahedron recurrence is exactly this morning what Rinat called the T-system for the SLN, except for the boundary conditions. And Spire observed that this T-system is satisfied by the partition functions of Aztec diamonds for a general weighting, namely for the two periodic you marked phases by A and B, but in this case you can actually mark every phase with a specific variable. So it's a huge generalization of the two periodic case. And actually the proof is very simple. It's basically the one that I gave for the Kuos argument. Spire in this paper even doesn't care to give a proof. It just refers to Kuos' article and invites the reader to adapt the proof for himself. So the Kuos the Kuos quadratic recurrence for the two periodic yields this quadratic recurrence. And in turn, this yields a very neat formula for the partition function of the two periodic Aztec diamonds. And again, to my knowledge, this was first given by Philippe and Rodrigo in 2014. Very simple formula. Now, what we want is the refined partition function. So we have to be able to compute the partition function when you fix the number of vertical dimers on the left boundary. So it turns out that Kuos recurrence also holds if you include boundary phases with weights x0, x1 up to xn. And the corresponding partition function I denoted by this, the NAB, and then those x variables. And you see that there's exactly one dimer adjacent to every boundary phase except this one. And this one is exactly the point where the dimers change from being vertical to horizontal. And that's exactly what we are looking for. So every configuration will get a weight which is this, except the xk, which will be missing. And so if you divide the full partition function by the product of all variables, all will cancel because of this term, except you'll get an xk minus 1. So you pick the coefficient of xk minus 1 of this ratio, and you get the quantity you are looking for. Now, the Kuos quadratic recurrence now reads in this particular case as this. So this is the general partition function with boundary phases here. And you see that there are two terms on the right-hand side. Each is a product of two partition function, and they have exactly the same origin as in the Kuos construction. You have two Aztec diamond of order n-1 this way or this way. And you can trace them very easily. This term is this one. And you see that this perfect matching of order n-1 it sees only these phases marked from x1 to xn. And then the next one, which is the one below it, it doesn't see any boundary phase, so that's just a normal boundary, a normal partition function. The next one is this one, and it sees only the n minus the n first phases from x0 to x minus 1. That's the dependence. And the last one, it doesn't see any boundary phase at all. Again, it's It's a normal, it's a standard 2 periodic boundary condition with no x's. And you can easily see why do you have factors here, because these altogether these four partition function will actually see every dimer except this let's see, except this one. You see, it doesn't. Wait, what did I wanted to say? Yes, yeah. Yeah, the X naught comes from the fact that the X naught comes from the other two. The X naught is here, not. So you see, these two, this one and the next one, they actually miss that dimer, and so it misses. They miss the weight X naught, and they miss the weight B that this dimer brings, and they also miss this dimer. So altogether, the two miss a factor of B squared and X naught. If n were to be odd, then this B would be an A. Okay, so you can actually understand very easily the formula and why these factors appear. So then it's not quite finished, but almost. So you get back to this recurrence that I have written on the previous slides, and then you consider this ratio instead. And if you consider the ratio instead, then instead of being quadratic, it becomes linear. It becomes linear. And so you have a linear recurrence of order 1 on k and on n. And so you can write fairly easily a generating function and compute the asymptotics of the coefficients. And the answer is this. So this is the result of the asymptotic. So of the asymptotic ratio. This ratio are the coefficients of the generating function, and by using standard methods, you can extract the asymptotic, and it's essentially given by this. That's the only among the few formulas that I will write. So F1 is known. F1 is known in terms of this function V, and the inverse function. So R of V is this explicit expression. I didn't say what R is. Ah, yeah, that's here. So the K, you want the K to be large in the scaling limit because you want the exit point of the upper path, of the uppermost path, to be somewhere on the western north boundary, but far away from the midpoint. So in the scaling limit, you put K equal to Rn, and R now becomes a real number between 0 and 1. So that's the first part. That's what the calculations you've got to make on the lattice. And the result is here. So the first problem is okay. Now we come to the second problem. And the second problem is to compute the slope of this straight portion. Now, a priori, it's not possible to extract the slope from a partition function. Partition function is just a weighted sum over configuration and doesn't know about the shape of what it describes. So you need further input. And the input is actually coming from the tangent method itself. I recall it. It assumes that the uppermost path does not affect the way the other n-1 path behave in the scaling limit. And this strongly suggests that to dominant order, the partition function actually factorizes into a contribution from the bulk part of the path, the n-1, and the contribution of a single path, which is that one, the uppermost forced to exit at a certain point. So you expect this kind of factorization. And this ratio Znk over Zn-1, that's what we have computed in here. So that is known. So what we need to compute now is this piece. So you need to compute the partition function for a single path now. And if you succeed to do that, then you try to extract the slope from the equality. Sorry? Yeah, so this almost equality means exactly that. So the exponential rates should be equal. That's not proved, of course. I mean, that's supposed to follow from the tangent method assumptions themselves. Yeah. So that's a maybe I'll just talk. It's not going to talk. So there's no proof, of course, and we just checked it in a number of cases, and it actually works. So we checked it for, I think, the Aztec period, the Aztec diamonds, the alternating sign matrices, and perhaps another few cases. And it always, I mean, somehow it is expected. It's the kind of expectation you have from the tangent method. So it's slightly reformulating it. So now we are up to computing this guy. But now, since we have decoupled this single path from the rest, then we let the rest do what they want, and what they want is to form the Arctic curve. And so the poor single walk here, what he sees is an empty region, which is bordered by the natural boundaries of the system and the Arctic curve, which actually you don't know, but you'll see in a moment how actually to know it. So this path, we imagine that it travels from the prescribed point P to the ending point Q in a completely empty region, but confined in a non-trivial region. Okay. Now it's not too difficult to show that the partition function for such a single path going from P to Q is exponentially dominated by the lattice path, which condense on a deterministic trajectory F. And in particular, the F is the shortest path between P and Q. And in particular, it's straight from P to a tangential point, and then follow the Arctic curve and straight down to a Q. We can also compute the contribution of this lattice, the combined contributions of the lattice path which condense on F, and it's given by this. And it's given as kind of action which is which depends on so far unknown function L. I'll just tell you in a moment what this function L is. So that we have, once the L is known, in principle we know that the partition function for this single path is this, a known thing. Now, we combine the two results. This is the lattice, this is the result coming from the lattice, and this is the result coming from the previous slide. S is an integral of L over F prime, and F prime is the red curve here. It contains a straight part on which the derivative of F is constant. So you just get a first piece from P, which is parameterized by this number R, to the tangent point on which F prime is constant and equal to the slope of the straight line, which is actually the value of the tangent of the Arctic curve at that point. It's the point where the straight line hits the tangential curve. So the slope T star is the derivative of the Arctic curve at this point. And then there is another portion which takes the integral of this L function of H prime, where H is the functional dependence of the Arctic curve. And this is constant. So this term is just this constant, and you have the integral as a second term. Now, the only dependent in the only dependence in R which parameterize the point here is in X star, because of course X star is the apsis where the straight line would hit the Arctic curve. Of course, it depends. It appears also implicitly in T star, and again only in the lower bound of the integral. So if you care to differentiate with respect to R, you get this very simple equation. All the integral, I mean, the only integral disappears. And that's what you actually are after, because here is an explicit relation between the slope T star and the parameter that parameterizes the position of this point. So if you can extract from that T star as a function of R, you are done. And of course, you've got to know this L function. So the only point that is left is to compute the L function. And the L function, as was expressed here, the L function actually controls the combined contributions of all the lattice paths that condense on F, And since we talk about lattice path, we've got to understand how those lattice paths now get weighted for the two periodic measure. So that will be almost the last piece. So remember, we have this bijection between the dominoes and the path. And for the uniform measure, we just have that the number of those two sets are equal. But now we want to extend this bijection in order to preserve the two periodic measure that is on the dominoes. So we've got to find the correct way to weight the path so that the weight of a set of paths is equal to the weight of a domino tiling. Now, that's not such a big deal. We know that the four varieties of dominoes, they get weight A or B depending on their positions. And they are, at least these first three, they are associated to an elementary step. So the weight of the dominoes will depend on their position, and therefore the weight of the steps will depend on where the step is taken. And here are two examples. If you step from here to here, which means that there is a domino, a blue domino here, then this step will get weight B. If you make the same step, but in this relative position, in this position relative to the A and B faces, this step will have weight A. And it's not very difficult to keep track of when is it B and when it is A and when it is B. I mean, the structure is two periodic, so it's not it's not so difficult. The only slight tricky thing is that the green dominoes, they contribute to the weight of a domino tiling, but they carry no step. And therefore, it seems to miss the weight brought by the green dominoes. And then there's a simple observation to go around this problem is that it's not difficult to show that for any red domino of type A, there'll be a green domino of type A. And for each red domino of type B, there'll be a green domino of type B. So you can sort of transfer all the weights of the green dominoes onto the red ones by squaring the weights of the red dominoes, because you know that the number of A or B type red dominoes is the same as the number of A, B type green dominoes. So you can forget about the green dominoes and push all the weights on the red ones. So that instead of giving the elementary steps weight A and B, you do give them weight A or B if they are diagonal weights. But if it's a level step, then you give a weight A squared or B squared, depending on where the step is taken. It could, yeah, you could do that, and indeed it seems to work. If you make an up step and then a down step, you get the factor b squared, and that's exactly what you would get here. That has to be justified somehow, because you still have the problem with the no step domino. What do you do with them? Well, yeah. But well, if you don't make sure that what you say is exactly equivalent to forget about the green dominoes, that's fine. But that's basically the argument that I gave here, I think. So right, then the next step is first start with a single path going from, say, the origin to a given point ij. And this path is made up of these 3 elementary steps. And these steps have weights a or b, a square of b or b squared, depending on the position of where the step is taken. Now, again, for a random walk like that, it's not difficult to write a recurrence relation and therefore compute the generating function for these numbers. And you get that. And again, standard techniques allow you to compute the asymptotics of these numbers. And the asymptotics of this number is exactly the L function. Now, I'm a bit late, so there was an argument here as to why this L function, which controls the asymptotic of the partition function for a single weight, for a single path, with no constraint except for the initial and ending point, also controls the combined contribution of all the paths which condense on a given function f. But the argument is essentially to discretize the function f and to a window of scale large to 1 but small to n. So a good choice is square root of n. On each piece here, this result is valid. So you take the product, that becomes a sum in the exponential, and you get a Riemann sum that becomes the integral. So now we've got everything we need. We've got the L function. I didn't write it, but it's explicit. You can compute it explicitly in terms of the form of the generating function. And you come to the final result. So I skipped the calculation of the parametric form of the actic curve in terms of the slope and then in terms of the parameter. But here is the final result. V is the new parameter. I trade the parameter R for a new parameter V by convenience. And beta is the ratio of these 2 weights A and B, which alternate on the graph. And it's a fairly simple form. And as a check, we can compute that. We can check that the U and the V, which are the 2 natural combinations of, well, that should be a Y. That should be a Y here, because the X and the Y only differ by this sign. So it's a natural thing to compute this, to consider these 2 combinations, and these 2 combinations satisfy the expected degree 8 algebraic equation. So as I said, this algebraic equation was first derived by Philippe and Rodrigo. It was re-derived by Chita and Johansson in 2016 by other methods, and re-derived again by another method by Deutz and Keulaars in 2021. And these 2 contributions rely on calculation of the Castellane matrix entries, inverse Castellane matrix entries. And if you take this parametric form and you vary the parameter V over the real line, you get the outer component here. This outer component is the outer component of the real section of this algebraic curve. And but if you plot the real section of this algebraic curve, you get also an inner component, which tends to fill the whole space when the parameter beta grows. And you see that the picture that I show at some point in a previous slide, which is a typical, generic configuration for the 2 periodic Aztec diamond, clearly resembles this curve. So we again guess the inner component with a sort of cusps. So we recover unexpectedly. We recover the known result, but the method somehow is is new. It's not new, but the derivation is new and relies on the tangent method. So that was the. So I flashed just the last. If you want to have a few references of what I said, the details of what I told you are this soon to appear submission.
Okay, thank you.
Thank you.
We have time for a few questions.
What would have prevented you from using the more standard tangent method? Because you already know this refined partition function.
That's right.
So you could move
Sure.
the end of the path away and then have to compute this second partition function, right?
Okay.
Of a single path.
Nothing would have prevented me from doing that. I forgot to say that was the difference with your approach.
Right,
you extend the domain, and the extension of the domain requires to solve a saddle point method. Okay. That's the only difference. And this approach, first of all, avoids this calculation, and in my opinion, also highlights the role of this L function, which I find nice.
So I have a second question. In this paper with Soto Garrido, we also actually treated the case of a more general periodic boundary conditions, which are 2 in one direction and 2n in the other, I think. And we have more of those Arctic curves with many blobs in them, etc.
Yeah.
Do you think you can just apply the same method here to these more complicated weights?
I just had a little thought about that, but I have no conclusion at the moment. So it's not impossible.
Okay. Okay.
Yeah.
So, I mean, just for the very last slide, I mean, this was a little bit fast.
Yeah.
How do you say that you can, by the tangent method, get the interior facet? I mean,
sorry, what?
Why do you get the interior facet? I mean, I thought the tangent method just gives you the outer facet.
So actually, in the tangent method, you always get only a portion of the Arctic curve.
Yes.
And in my parameterization here, the V goes from 1 to infinity and only gives you this northern part. But now you extend, just to see what it yields, you extend the variation of the parameter over the real line. Oh, you draw it and you get the full outer component. Okay. Then you say, okay, this parameterization satisfies this algebraic equation for any V, even complex.
Okay.
So you get the algebraic equation, and from there you draw again the real section, and you discover that the real section has 2 components, and the inner component is not accessible with the tangent method. Okay. It comes for free somehow.
I see. Okay, then if I may also ask, sorry. So this is a general question, which presumably you are being asked sort of almost every talk. But the question is, with the tangent method, I mean, do you have any chance to handle shape fluctuations? The facets are deterministic. I mean, your x-axis curve is deterministic, but in actual fact, it's fluctuating and so.
Sure. Yeah. Yeah. At the moment, we have no answer to the fluctuations, of to what the fluctuations are. That's probably the next question, but.
I keep asking the same questions, but probably here is also relevant. Can you tell anything about the power laws of your inner shape? Yeah. That's first question.
Yeah, like my
and also anything which distinguishes. It looks like they clearly have a fluctuating phase inside, and a more frozen phase. So really in the center. So is anything known about the correlation functions, because it looks like there are short range outside, probably long range or power law in between, and probably some kind of
it's exponential. Yeah. So so for the first question, like my predecessors, I have not computed the exponent, but this is the Arctic curve. This is a circle, so the exponent will be something like 2, and it will actually increase as beta gets larger, because the profile here gets flatter and flatter. So I expect that it becomes. You were talking about the cusp. No, I don't know. I haven't looked at it. I mean, it would be not difficult to just look at the dimensions of the cusps. And for the second part, which was about the behavior of the correlation functions. Yeah, it's power law here in the in between phase, and it's exponential in the interior. Yeah, all here, all. I mean, I guess so. You should check one of the last paper by Johansson, who examines exactly the behavior of the inverse Castellane matrix exactly at this border between the inner and the in-between phases. I guess it is known. Yeah.
Exponential.
Yeah, but the correlation length. Yeah. Yeah.
May I go?
Sure.
Yes, I would just wanted to add one comment, that the extension of a portion of that curve analytically to the whole curve only works at 3 Feynman case. Okay. And then I have a question. You see, the spikes over there are yes, the spikes of the antiferro region, let us say. You know, there is a change in direction. There are, in the last slide, I don't know if it's a mistake or what. They are along the diagonals, not along the medians. So what's the point there? It's a mistake.
I may got the picture wrong. Yeah. I forgot to rotate it.
Okay, fine. No, I was wondering if at there was some critical beta which was completely new for me.
No. So thank you for noticing, because actually the curves were computed with Mathematica and the frames with Keynote, and I had to match the. I have to rotate the Mathematica figures to fit in the frame. So I forgot to do it on the last figure. Thank you.
If there are no further questions, let's thank again Philippe.
Thank you.
We resume at 3:45.